Hello children, welcome back to the channel. Today we will be continuing our discussion of moment of inertia. In our previous video, what we had seen is that moment of inertia was given by this expression I equal to summation I to n mi ri square, where mi's are the masses of different mass points and ri's are their respective position vectors. Now if we consider a special case where let us say this is a rigid body and this is a given axis about which it is rotating, okay, and let us say this is R1, this is R2, this is R3 and so on. However, what we have considered here special is that all the mass points are equal, that is instead of M1, M2, M3 etc. we have all M's here. So moment of inertia by definition will be given by M R1 square plus M R2 square till the nth particle, the last particle, that is M Rn square. All the particles have the same mass. All the particles of the rigid body have the same mass. So what we do is that we can take M common out of it. We have R1 square plus R2 square plus till Rn square. Okay. Now if I multiply this by n, number of particles by number of particles, that is we are multiplying it with unity. So what we will get is that m into n, then we have R1 square plus R2 square till Rn square, whole thing divided by n. Or we can say m, since total mass of the rigid body will be m times n times n number of particles having a mass m, so total mass will be m into n, right? So total mass of the particle will be equal to m into k square, where what we have taken that m equal to small m into n and k equal to r1 square plus r2 square till rn square, whole thing divided by n, and then this. So what does this expression signify and what does this expression signify? What is this and what is this? First let's get to this. What is this? This is actually, see, R1, R2, R3 are the distances of the particles, right? So R1 square, R2 square, R3 square are the square of the distances, right? So R1 square, R2 square is square of the distances, square distances, right? Square of the distances. Now if I take R1 square, R2 square, R3 square, whole thing divided by n, then what we get? We get mean of the square of the distances. So this is mean of the square of the distances. However, k is not equal to the term under the square root. It is actually k equal to square root of the term or square root of the mean of the square of the distances. So k is actually known as root mean square distance. So this k is known as the root mean square distance of the particles of the rigid body. Now what does it actually physically signify? See, if this expression says that I equal to whole mass of the object into root mean square distance. Now we already know that since it's under a square root sign, this k will have the same dimension as distance. So k square or k will actually represent certain kind of distance. So this expression means that if we have a particle of mass m situated at a distance of k, this distance is k and this is m, then this particular mass m, which is equal to the mass of the entire rigid body rotating about the same axis of rotation, if we have entire mass of the our rigid body concentrated at a point k, and the point's distance from the given axis of rotation is equal to k, then this point mass will have the same moment of inertia about the given axis as the entire rigid body. Are we clear? If the entire mass of the rigid body was concentrated at point, say whatever point we call this, let's call point P, which is at a distance equal to the root mean square distance, that is equal to K, then the entire body, that particular point mass P will have the same moment of inertia as the entire rigid body with the distributed mass. Okay, now this term K or the distance K has a particular name. It is known as the radius of gyration of the rigid body. So radius of gyration is nothing but the root mean square distance of the particles of the rigid body from the given axis of rotation. This we will be finding in our a little while later in our discussions when we try to find the moments of inertia of different fixed shaped bodies about give certain axis of rotation. That we will do in a while, probably in the next video onwards. Okay. Now, as the moment of inertia dependent on the mass distribution and the axis and all, so radius of gyration also depends on the position and orientation of axis of rotation. This. So, if K is the radius of gyration for this given axis, if the axis was somewhere here, parallel axis, or if the axis was perpendicular to the board, then the radius of gyration would have had different values. This is one, depends on position and orientation. Position, that is parallel axis, different away or closer to the body, we will have different radius of gyrations, and if orientation, if it was perpendicular, it was some angle some other way, perpendicular to this also, then we would have different radius of gyration. And of course, it depends on the distribution of mass. So, if the masses were closer or the shape of the rigid body was different, so the mass distribution would have been different, and so the radius of gyration would have been different. Okay. Now let's move on to theorem of parallel axis of moment of inertia. So, what does this theorem say? First, let's consider we have a rigid body of mass m, and we want to find the moment of inertia of the body about an axis PQ, as shown in the diagram here. So, to do this, what we will do, we will first try to find the moment of inertia of a mass particle somewhere having a mass small m. Say capital M is the mass of the rigid body. So, we will consider a particle of mass small m at certain distance from the given axis, and then find its moment of inertia, and then what we will do, sum over the entire body to get the moment of inertia of the body about the given axis. Now, to do so, let us consider another axis RS, which is parallel to the given axis but which passes through the center of mass of the body. So, let us say we have another axis like this parallel to PQ, and this axis, let's call it RS, and this passes through C, the center of mass of the body. Okay, and let's assume that the distance between the given axis, two axes, becomes D, and the distance of the mass point M from the center of mass is X. So, the moment of inertia delta I about PQ for this mass point M will be simply mass of the particle multiplied by D plus X, which is the total distance of the mass point from the given axis, and squared. Right. So the moment of inertia of the entire body can be given by I about the given axis PQ will be summation m d plus x whole square. So let's open the whole square term. We will have three terms: summation m d square plus summation m x square plus summation m 2x d. Right? D square plus x square plus 2xd, d plus x whole square. So let us now consider the three terms separately. First term is summation m d square, then we have summation m x square, and then we have summation of 2m xd. Fine. Now for the first term, what we need to notice here is that d is a constant distance. The distance between the two axes is the same. It will not change because we have already chosen them. It's a fixed distance. So d can come out of the summation sign. So it will be d square into summation m. But summation m is the sum of all the mass points of the rigid body whose total mass is m. So summation m will give us the total mass of the rigid body. So we will have this is equal to m into d square. Second term, summation mx square, is simply moment of inertia of the body about the center of mass. Right? X is the distance, m is the mass particle. So if we sum over the entire body, we will get the moment of inertia about the center of mass, and x is passing through the center of mass. Now for this term, this can be rewritten as 2md, which will not 2md, 2d, since d is a fixed distance. 2d into summation m into x. Now we need to notice the very important property of this m into x, or center of mass. What is mx? Mx is nothing but mass into distance of the object from the mass particle from the center of mass. Now, or in other words, moment of the mass. Now center of mass we know is a point where, if we consider entire body's mass to be concentrated, it will behave as the entire body, right? Which means that center of mass is a point about which the entire body's mass will balance. In other words, for every x, m into x on one side, there will be an mx in the negative x direction or in the negative side of it, so that these two will cancel each other. What we are trying to say is that since the entire body's mass will balance about the center of mass, so the sum of moments of masses about the center of mass has to be 0, which means this term has to be 0. So this will be 2d into 0, that is 0. So we have evaluated all the three terms, md square, summation mx square, and this one, right? So what we get is that, therefore, the I can be given as summation mx square, that is I cm plus m into d square. This is the mathematical statement of theorem of parallel axis. In words, what we will be able to say is that the moment of inertia of a rigid body about a given axis is equal to the sum of moment of inertia of the body about an axis parallel to the given axis and passing through the center of mass, and the entire mass and the product of entire mass of the body and the distance between the two parallel axes. Since we are considering parallel axis here, that's why this is known as the theorem of parallel axis. So the given axis, if you want the moment of inertia about the given axis, what we'll do, we will find the moment of inertia about the center of mass and then add it with the entire mass of the body multiplied by the distance between the two given axes. Okay, the next point or next theorem is the theorem of perpendicular axis. Now the previous theorem, that was the theorem of parallel axis, was applicable to any kind of bodies. However, this theorem of perpendicular axis that we are going to discuss will be applicable to plane lamina, that is a body which thickness is very small and which lies in a plane. Let's consider we have a plane lamina like this, which is lying on the xy plane, and we want to find the moment of inertia of the plane lamina about an axis which is perpendicular to the plane of the lamina, that is along the z axis. So if the lamina is lying on the plane of the board, the axis will be perpendicular to the board. Okay, so we have shown the three-dimensional, so we have drawn it this way. Now to find this, what we need to first consider is that similar to the previous case, that we considered a point somewhere at some distance. Let's call this here P, whose coordinate is xy, or whose distance from the origin, that is the z-axis, is r. Okay, so if we draw perpendiculars from this point to the x and y axis, then this y axis will be x and this will be y, or this distance will be x and this distance will be y. So what we will do is that if we look at this, since this is 90 degree and this has to be equal, so this will be x. So from the geometry of it, what we get is that r being the hypotenuse for a right angle triangle, what we get is r square must be equal to x square plus y square. Okay, now if I consider this particular point, what is its distance from the x-axis? Its distance from the x-axis, if we consider, will be along this. So this length is equal to y. So the distance of the point P from x-axis is y. Okay, now let's consider there is a small mass of m, small m. Then the moment of inertia of this particular point, mass situated at point P, will be about the x-axis, will be given by my square. That will be, of course, delta, that is for the particle. For the entire body, Ix will be summation of m y squared. Similarly, if we consider the moment of inertia about y-axis, it will be summation of m into x squared, because the distance of point P from y-axis will be given by this line, which is x. Okay. Now, what is the moment of inertia? We want the moment of inertia not about x and y axis. We want the moment of inertia about the z axis, which is perpendicular to the plane of the lamina, which is lying on the xy plane. So Iz that we want to find will be equal to summation of m into r squared for all r squares and for all m's, that is for all mass points. So this is equal to summation m into y squared plus x squared from here. Or we can open this up and say that this is equal to summation m y squared plus summation m x squared. So this equation 1 and 2, if we substitute the value of summation of my square and mx square in here, what we get, Iz, that is moment of inertia of the plane lamina about an axis perpendicular to its plane, is equal to Ix square, Ix plus Iy. That is equal to the sum of the moments of inertia of the body about two perpendicular axes lying in the plane. X and y axes are perpendicular to each other. So two perpendicular axes lying in the plane of the lamina and meeting at the point where this perpendicular axis meets the lamina, that is the origin here. So moment of inertia of an axis of a plane lamina about an axis perpendicular to the plane of the lamina will be equal to sum of the moments of inertia of the same lamina about two axes which are mutually perpendicular and lying in the plane of the lamina and which meet at the same point as the perpendicular axis meets the lamina. So since these are three mutually perpendicular axes and this expression gives a relationship between moments of inertia about three mutually perpendicular axes. That's why this is known as theorem of perpendicular axis. These two theorems are very important and going to be very important when we try to solve problems and find moments of inertia of different bodies. That we will be doing next. Okay.